Okay. And there we go. We're off. Welcome back to another lesson. Today we're going to talk about Pythagorean theorem and its converse, okay? And since this is probably mostly review for a lot of you out there, we're going to work on the mechanics behind Pythagorean theorem. Throws in some newer concepts that you might not have seen before. We're going to do this in two parts. So part one is just mostly a review. Part two, we'll talk about some inequalities and how that kind of relates and ties into the Pythagorean theorem. Here's a nice picture of Pythagoras right here, the guy responsible for this lesson, and a lot of pain and hardship for maybe some other students. No, just kidding. But let's go ahead and jump into it. From what you remember back in your earlier days of mathematics, the Pythagorean theorem is summarized as follows. We have two legs of this right triangle, and if we square each measurement, add the results, it will equal the hypotenuse, which would be C. A, B, and C is just a typical main mechanism for this theorem. It would equal C squared. Okay. Now, what's very important is, as you probably dealt with in the past and discussed it, that the Pythagorean theorem only works for right triangles. Okay. If you use this for any other triangle out there, the measurements will not work for it. Okay. So it's actually a very unique situation when it comes to that, and we're going to use that information to our advantage in the future as well. Okay, so let's just dive into one question. Okay, just to kind of start us off, and let's look at this. Let's do this guy. All right, here we go. Let's do 6, 15, and blank. Okay, I don't know what the hypotenuse is. I could use C. I know a lot of people use A, B, and C. Oh, why not? I just convinced myself. We'll use C. Now remember, the legs are here. The hypotenuse is always the largest side. It's also diagonal to the right angle. Okay, another characteristic, just in case you don't have any measurements, you can at least locate where that guy is, besides visually looking at it as well. All right, so here we go. Using the following theorem, we're going to plug these values right into here. Okay, so here we go. 6 squared plus 15 squared equals C squared. Okay, now we are going to solve for this, but first we have to simplify this side first. So 6 squared would be 36. 15 squared is 225. Okay, that'll be my first step, simplify the exponents. Okay, the next step would be to combine this. We get 261 equals C squared. And if you remember from your algebra days, to get rid of the exponent here, because C isn't by itself, there's technically like two C's being multiplied here, we would take the square root of those sides. And that's going to cancel out the exponent here. So C is roughly 16.2. Okay, that'll be the dimension for it. Let me just get a quick side note, and I'm sure a lot of you delved into this, but the reason why that cancels, if you remember, a square root can be written as an exponent. Okay? If we have a cubed root here, it'd be C to the 1/3 power. Okay, and if we have a fourth root, it'd be C to the 1/4 power. Okay, and if I want to get rid of this, I could square this guy. I would cube and I would raise this to the 4th power. Okay, and when I square something or raising it to a power, I'm multiplying the exponents, so this just becomes C. Okay, that's what's happening over here. Now, when I take the square root of this, what I'm technically doing is I'm raising it to the 1/2 power. 2 times 1/2 is just C to the 1st power. Okay? Just a little side note in case you're just thinking, wait a minute, why does that work again? Okay? Just go back to exponents and rules of exponents to figure that out. We could check our work. We could always plug it back in. But remember, the hypotenuse is the largest side. 16.2 is larger than these guys. Okay, so it's within relative reason that this would be the correct answer. Okay, let's try another problem. All right, So I don't know this side length, but I know this is 9 and this guy's 15. I'm going to try to find the missing measurement. Well, you can see there's going to be a difference here. This one was just the hypotenuse. This one, I'm missing a leg, right? The hypotenuse, which is diagonal to this guy, okay, hypotenuse, the C value, is the largest side, and that's this guy, 15. So let me go ahead and plug these values in. It doesn't matter what A and B are because when we add, addition's commutative, doesn't matter the order. We have 9 squared plus x squared equals 15 squared. Okay? So already you can see the difference. We have 81 plus x squared equals 225. Now, unlike this guy, I had to add these up, take the square root. Now over here, I don't have that luxury. I have to simplify x squared by taking the 81 to the other side by subtraction. I get x squared equals 144. And then just like we discussed over here, taking the square root to both sides would isolate the x here. So we get the answer to be 12 for that guy. Okay? And we could check. 12 is not larger than the hypotenuse. So we could say within the relative realm of reason that this is good, plus we could always plug it back in to see if it works. Now, these two examples I picked specifically because you can see that there's something going on here. With this example, I had a decimal value. With this example, I got a whole number. Okay? In fact, we can see that 9, 12, and 15, okay, if I change this to a 12, I can see that this will satisfy the Pythagorean theorem. When I plug this into here, it will still satisfy it, but it is a decimal. Okay? So here's the deal. Anytime we have whole numbers that fit perfectly into here, we call those Pythagorean triples. This would not be because it has a decimal. Okay? Let's just dive into the definition real quick. We'll go back to the PowerPoint. Okay? So the Pythagorean triple is a set of 3 non-zero whole numbers that satisfy this guy right here. Okay? Like I said, could you get a decimal in there and still satisfy it? Absolutely. But a whole number is the key part here. So we categorize those as Pythagorean triples. Okay? There are a ton of them, an infinite number. Here's just some of them that are out there in the world today. Just to kind of tell you how this is working. For instance, let's take this guy. The first two numbers are the legs. The last number is the hypotenuse. So if I do 11 squared plus 60 squared, it will equal 61 squared. These three would work perfectly. Okay? Now, here's the interesting part. Go back to this for a second. Okay? If I take this triangle and I double everything, let me make this 18, make this 30, and make this 24. Because I multiply everything by the same scale factor here, by 2, okay, this is still a Pythagorean triple. I could still plug these in to the Pythagorean theorem, and it will still work, okay? See how I said there was an infinite number of these? There really is. As long as I multiply all the side lengths by the same scale factor, I can get a new Pythagorean triple. Okay? Does that make sense? All right. Now, looking at this example here, we're not going to solve for a side length. Instead, we're going to figure out what the missing side length is based on if it's a Pythagorean triple. Okay? Now, I'm telling you ahead of time they are. Looking at the first one, we have 5, 12, and then blank. And the last one's a 3, 4, and then blank. All right? Let's take a look at the previous slide. So let's see. We have 5, 12, oh, the missing side length would be 13. The next example was what? 3, 4, so the missing side is 5. Okay? So the missing parts would be 13 and 5. This is good, okay? Because I know a little bit about how these numbers work and how they work with the Pythagorean theorem, that's less time, right? Less measuring in a way, if I know that those side lengths will make my right triangle, okay? So Pythagorean triples, very useful tool. All right. Let's talk about the converse. And that's it. Okay, I think that'd be a good first part 1 of this lesson. Okay. All right. Now the converse is found by switching the hypotenuse with the conclusion. So here's the deal. Okay, we stated that you have to have a right triangle for a squared plus b squared equals c squared to work. All right. Now the converse is flip that. If a squared plus b squared equals c squared works, then we have a right triangle. Okay, that's what the converse means. Okay, so let's go ahead and try a problem out to kind of cement this idea. And we'll try this one. Okay. All right, here we go. Now, what I'm trying to do is I want to prove, I'm going to put a question mark here. I'm going to try and prove that this is a right triangle by seeing if the Pythagorean theorem works for it. Okay? Now, these are the legs. If I go diagonal from the right angle, that's my hypotenuse. If you want to label, you can A, B, and then C. So we have 12 squared plus 9 squared equals 15 squared. Okay? Simplifying it, this would be 144, 9 squared is 81, 15 squared is 225. Add these guys up together, I get 225, and hey, it works. 225 does equal 225. In other words, yes, this is a right triangle. These could be decimals. That's fine. It doesn't have to always be whole numbers. But when I plug them into here, if the left side equals the right side, then yes, this has to be a right triangle. Because remember, Pythagorean theorem only works for right triangles. Okay? Could you solve this differently? I'm so glad you asked that question. You can. All right. So let me do this. Remember Pythagorean triples? Okay? Look at 12, 9, and 15. They have an element in common, right? If I divide this by 3, actually, if I divide all sides by 3, look what happens. This reduces down to a 4, this reduces down to a 3, and this one reduces down to a 5. Hey, how about that? This is actually a 3, 4, 5 triangle. It's a multiple of a 3, 4, 5 triangle. And just based on that information, I could say that, yeah, this is going to be a right triangle because Pythagorean triples always work for this. Okay? 3, 4, 5 is a very common, a very popular type of triangle out there, and it has a lot of uses for it. Just seeing that that is a 3, 4, 5 triangle does a lot for a application problem, I could say. Okay? So this is the converse. If this works, then this must be a right triangle. Okay? Alrighty, guys. And that's it. That's it for part 1. So like I said, it's kind of a review of what you've discussed in the past. So I just wanted to make this lesson video as small as possible. Hope you're doing well. My notes are online, so feel free to look at those through some of the other examples, and we'll do part 2 later on. So hope you guys are having a good day, and I will see you all in the next lesson video. Take care.